Hi, chemist. Dr. Ross here with chapter 2 of our introductory general chemistry course, or Chem 65 as we call it. The contents of this chapter, which looks at measurements, are as follows. Standard and scientific notation. We're going to look at units, significant figures, rounding, dimensional analysis, temperature, and finally density. Okay, so standard notation, this is just regular numbers. So for example, on the left over here, we have a number 527,500. So any regular number that you're familiar with, that would be standard notation. On the right, we have it in scientific notation. Scientific notation is a tool that helps us deal with large or small numbers that might be cumbersome to write and impossible to enter into a calculator or something. We convert the standard notation into scientific notation by making a number between 1 and 10 and then multiplying it by an exponent 10 to the power n, where n can be positive or negative. So for example, this number here, 527,500 feet, it equals 5.275 by 10 to the 5 feet. Notice that the 5.275 is a number between 1 and 10, and the exponent by 10 to the 5 tells us to take the decimal and move it 5 places to the right because the exponent 5 is positive. If we were to insert the decimal here between the 5 and the 2, and then move the decimal 5 places to the right side, indeed, we would have reconstructed the number 527,500. Okay, if we take a look at a second example, we've got 0.0000424 liter. This is a number less than 1. So we're going to have to make this number between 1 and 10 as our scientific notation dictates we have to. So that must be 4.24. And then we multiply it by 10 to the negative power. Negative means we would eventually have to move the decimal place to the left again to give us a number less than 1. If we were to put the decimal here between 4 and 2, and then move it 5 places to the left, then we would generate the original standard notation number. Units. So whenever you record a value, you're going to probably give 3 things: a description of what the object is, the magnitude of the object, and the unit that the magnitude is representing. So for example, if you have some iron filings over in the corner of the room, you might want to know, okay, now I know it's iron filings. How many are there? Okay, there's 100.00. Okay, great. 100.00 what? Kilograms. Great. So I've got 100.00 kilograms of iron filings. Excellent. Morphine. How much morphine do I have? I have 0.00197 microliters. Great. Water, I have 56.4 degrees Celsius water. Sodium chloride, here I've written it in scientific notation. I've got 3.1 by 10 to the negative 2 moles of sodium chloride. Excellent. Hydrogen, I have 0.976 atmospheric pressure of hydrogen. Excellent. So naturally, you would give these 3 pieces of information associated with a unit. So make sure you're on the lookout for these 3 pieces of information. The metric table, so this is a generic metric table. I would say these are the important ones. This is not an exhaustive list, but I would definitely encourage you to commit a list like this to memory. I would learn them in pairs. So for example, tera is 10 to the 12. This is trillion. Pico is 10 to the negative 12. This is trillionth. I would learn those together as a pair. Giga is 10 to the 9. That's billion. Nano is 10 to the negative 9. That's billionth. I would learn those as a pair. Mega is million. micro is millionth, kilo is thousand, milli is thousandth. I would land those as a pair. And then a couple of odd ones here, just because they're common. Deci is a tenth, and centi is a hundredth. I would just learn those as two odd additions. Significant figures. So significant figures are important numbers, numbers that have meaning. Insignificant digits are numbers that have no meaning, but you keep them around until you're about to produce the final answer. We have to keep track of significant figures, therefore, during calculations. So if we are going to multiply and or divide, we have to propagate fewer significant figures. So for example, if we are going to calculate the volume of an object, and here we can see that volume is the length times the width times the height of the object. And let's say we've measured the length to be 32.0 feet, which is 3 significant figures. We've measured the width to be 13 feet, which is 2 significant figures. We've measured the height to be 8.04 feet, which is 3 significant figures. We see that the least number of significant figures is 2 significant figures. Therefore, when we take the product of all of these measurements, we have to record 2 significant figures eventually. To do so as an intermediate step, we write down all of our significant figures, which here is 2, and we also write down 2 insignificant figures. The dashed line represents the boundary between significant figures on the left and insignificant figures on the right. So it's 3,344 cubic feet. Now we would have to round down to 2 significant figures, which we have here as a boxed final answer. The rounding rules are going to be on the next slide, I believe, but just briefly here, we look at the first insignificant digit and we notice it's less than a 5. That means that we add 0 to the last significant digit. So adding 0 to 3 returns the number 3. And then rather than write the insignificant digits, we write zeros to maintain the order of magnitude. If we were to just ignore them, we would convert 3,300 into 33, which is 2 orders of magnitude wrong. So we just add the zeros to maintain the thousandths of orders of magnitude. If we are going to add or subtract, instead of significant figures, we have to keep track of least decimals. Another way you can arrive at this is to look at the largest absolute uncertainty, but more about that in another video. For now, we're just going to keep track of the least decimal places. So let's say we're going to add 12.05, 21, and 120.8. We notice that the first number has 2 decimal places. The second number has 0 decimal places. The last number has 1 decimal place. So the least number of decimal places is the middle number with 0 decimal places. Therefore, when we add, we're not allowed to give any decimal places. So we add them up, we get 153.85. The dash line now goes right where the decimal would be, and we've written 85 because we get into a good habit of writing 2 insignificant digits. So now we have to round because we're not allowed to give any decimals. We notice the first insignificant digit is greater than a 5. That means that we add 1 to the last significant digit. So that 3 now becomes a 4. We can't give decimals, so we don't write anything after the 4. We've preserved the order of magnitude. It was order of magnitude hundreds. We preserved hundreds orders of magnitude. So we're done with 154 meters. Okay, here's the rounding rules that will follow. Again, it's always a good practice to give 2 answers, the unrounded value with a dash line that separates the significant figures to the left, and then 2 insignificant figures to the right of the dash line. And then finally, we give a boxed, fully rounded answer. So looking at the first case, we've got 456.343. We notice that the first insignificant digit is less than 5. That means that we add a 0 to the previous digit, which is the last significant digit. We preserve the order of magnitude, which is the order of hundreds, and therefore we're done with 456.3 grams. Case 2, we notice that the first insignificant digit is 5. We look at the second one, it means that because it's greater than 0, we know that the 5 is really greater than a 5. It's headed towards a 6. So therefore, we would round up. We add 1, not always. We add 1. We would add 1. Sorry, we always round up in this case. So we add 1 to the 3 to make it a 4. We preserve the order of magnitude, and we're done with 456.4 grams. Case 3 and 4, the first insignificant digit are both exactly 5. We confirm that by looking at the second insignificant digit. So we've got exactly 5. What do? We don't automatically round up. We round up only if the last significant digit is odd. So there's a rule that says if the last significant digit is odd, you round up to make it even. So we add 1 to the 3 to make it a 4, and we're done with 456.4 grams. Alternatively, in case 4, if we have exactly 5 and the last significant digit is even, we add 0 and leave all well alone. And again, we're done with 456.4 grams. Dimensional analysis comes by a couple of different names. You can call it factor labeling. You can call it unit line equations. It's essentially a method to do calculations that's promoted and used often in science classes. It uses equalities to convert input into output. So for example, if the question is to convert 958 feet into centimeters, then we look at what we want. We want centimeters. We immediately write centimeters as a numerator here. So we're going to construct the dimensional analysis backwards. So we look at what we want centimeters. We write centimeters initially as our first input going from right to left. We set that equal to something. We know that by definition, 2.54 centimeters is equal to 1 inch. How do we know that? We look it up in a reference table. So this is not something you'd be expected to know. But we know that these are equal to each other. 2.54 centimeters equals 1 inch, so that's an equality. Our denominator now is the preceding numerator, and then we look for another equality. We know by definition 12 inches is equal to 1 foot. The denominator foot becomes the preceding numerator, which is our input. So looking at the units, the feet cancel, the inches cancel, and we've just got a number of centimeters. We run the math. We ignore the significance of exact factors. So our input has 3 significant figures. That therefore limits the output to 3 significant figures. We do the calculation. We get 2.9199 by 10 to the 4 centimeters. The dashed line is after the third digit to remind us we have to eventually round to 3 sig figs. The first insignificant digit is a 9. That's greater than a 5. So we add 1 to the last significant digit, which is 1, making it 2. So our final answer is 2.92 by 10 to the 4 centimeters. Okay, temperature. There are 3 common scales of temperature that you might encounter in an introductory chemistry course. There is units Celsius, Fahrenheit, and Kelvin. Notice the Kelvin is the only one that doesn't have the degree symbol. Okay, so Kelvin, you can convert Celsius to Kelvin by taking the value in Celsius and adding the exact value 273.15 to it. So if you're looking at the, how many digits do I give when I convert Celsius to Kelvin, you just use the adding rules. So you're adding something with 2 decimals. So whatever your value is in Celsius, you're adding the least, you're basically going to give Kelvin that corresponds to the least number of decimals. So if you have Celsius with 0 decimals and you add a value with 2 decimals, you have to preserve 0 decimals because that's the least number. If you have Celsius and you want to generate Fahrenheit, you multiply by 9, divide by 5, and then add 32, and that will give you Fahrenheit. So again, hopefully that's straightforward. It would be expected that a student early on in an introductory chemistry class could be given a temperature in any one of these units and would be able to convert it to any other of these units. So I think I'll probably assign a homework or a quiz or something that will give you some practice. So meanwhile, I would recommend that you practice doing that. Density. So this will be the last slide of this video. Density is an important variable, an important property, sorry. It's the ratio of mass over volume of an object. It is an intensive property, which means it's independent of sample size. That makes it a constant. And it's useful because we can measure it in a consistent way. So let's look at a typical example using dimensional analysis to calculate something using density. So this question says, what's the mass in pounds of a 1.2 gallon of mercury, liquid mercury, atomic symbol Hg? And the given density of mercury is 13.53 grams per milliliter. So our game plan is as follows. We're going to construct this backwards, starting with what we want. So we want pounds. So we start off by writing pounds. And by definition, we would look this up in a reference table. A pound of mercury is equal to 453.59237 grams of mercury. That's an exact conversion. The gram denominator becomes a preceding numerator. Then we can use our density. 13.53 grams of mercury is equal to 1 milliliter of mercury. This is a measured input, so this counts as 4 significant figures from the numerator here. The denominator milliliter becomes the preceding numerator. By definition, or definition if you're being fancy, by definition, 1 milliliter is equal to 1 centimeter cubed. That's an exact conversion. Centimeter cubed is promoted as a preceding numerator. By definition, 2.54 centimeters cubed is 1 inch cubed. Inch cubed is promoted as a numerator. 231 cubic inches is a gallon, exactly. Gallon is promoted as a numerator, and we use our input 1.2 gallons of mercury. The only unit that doesn't cancel is pounds, which is our target unit. We've got 2 significant figure input. Exact conversions don't count as significance. We've got a 4 significant figure density. Because we're multiplying, we propagate least significant figures. In this case, it's 2 significant figures. Our calculator tells us 135.4 pounds. We've got our dashed line that separates the significant digits on the left, and then 2 insignificant digits on the right. We've got a 5 and a 4. That's going to be greater than 5, so we round up by adding 1 to the last significant digit. So that 3 becomes a 4. We put zeros where the insignificant digits are, up to the point where we preserve the order of magnitude. We only put 1 0 because it's order of 100 pounds. If we had put a second 0, it would be order 1,000. So we can't do that. So we have to keep it order of magnitude 100 pounds. So our final answer is 140 pounds to two significant figures. And that concludes this video.